we thought of covering is basically on coordinate system, time system, and satellite orbit. So we'll see how much in 1 hour we can cover on these two topics. So basically, when we as the hearing started with this thing that you have to processing these data set for the complete GPS thing. So the GPS concept takes this understanding that the satellites send certain signals, and those signals are modulated on a carrier. So we use carrier as well as the codes information which is available through the. But before these, what happens is since the satellite needs to connect to the receiver in a way that the position of receiver needs to be computed, knowing that satellite or you have the satellite position. With this understanding, the requirement of coordinate system comes is that you need to identify the coordinate, or you need to estimate the coordinate in a similar system in which you want the coordinate of your receiver. So for this, we start this understanding of coordinate system with we'll see little background and what are the relevant coordinate system and time system for the GPS. Then we go on to understand the different components as well as the limitation as advantages, and followed by application and starting information about the satellite orbits. So many people want to know which coordinate system are we working on, but before that, if you have to identify Cartesian coordinate system, because many of you in your 11th level or intermediate level you only understand the coordinate geometry. You don't understand about whether it is related with the earth or whether it is related with anything. You just have a coordinate. So understanding of coordinate in earth or on a surface of earth is just that the simplest coordinate system is earth centered, earth fixed. And one of the reason of having this earth centered and earth fixed coordinate system is that you don't want your position to be changed as the earth rotates. So the reason of having the simplest coordinate system which fixed with respect to the earth and centered at the center of mass of earth. So with this concept, we started this simplest coordinate system which is earth centered, earth fixed, and its origin at the center of mass of earth, and the three right-handed orthogonal axes are x, y, z. So just you don't need to worry about how the x, y, z are there, but the three components. So whenever you define a coordinate system, you need to define its origin, you need to define its fundamental axes, and you need to define the scale. So in doing so, the units are in meter in this ECEF system, but the z-axis coincide with the earth mean rotation axis. So as sir said, you have a very vibrant polar motion. You cannot, your axis is not consistent. Your axis is not static. You have to consider the mean rotation axis to point a particular axis. So this ECF system, we assume or we consider that z-axis coincide with the earth mean rotation axis or points to mean pole, followed by the x-axis which points to Greenwich or zero meridian or reference meridian. The xy plane called as mean equatorial plane, which you could see from this. This is your mean equatorial plane, and xz plane which contains the mean pole as well as the reference meridian or call it prime meridian for taking the measurement. So these are the fundamental planes which are defined for the ECEF. Similarly, the geodetic coordinate system can also be established based on this ECEF, which is nothing but where we have to project a normal to the ellipsoid, normal to the surface, and that meet on equatorial plane, and this phi and this lambda, which we call it longitude and latitude for those points, and obviously this is the height. But since it is not a very easy way to understand, we need to consider the earth surface also, how we model the earth, so that this phi, lambda, and h could be realistic. So that's why in detail, the geodetic longitude is nothing but the angle between a reference plane and a plane passing through that point, both planes being perpendicular to the equatorial plane. So that's how we define the longitude, and similarly the latitude also from that equatorial plane to the vertical direction. So this is only possible if we define the earth shape, and the shape are defined based on certain parameters. So we are more interested, we are not talking about the details of how ellipsoid has come up, how geoid was there, but we need to understand the mathematical understanding of the shape, which is nothing but the flattening, the major axis and minor axis. So this is how we relate this, this particular system by understanding these parameters. So the simplest understanding of defining a coordinate both in x, y, z as well as on the lambda phi h. We can convert these two also in between, so that if we have x, y, z, we can go on to have a geodetic latitude, longitude and height information of the same point, or if we have x, y, z, you can go on a conversion. So we are not interested in this conversion in this lecture, but it is possible. You can convert from geodetic latitude, longitude, height to the ECEF x, y, z. Similarly, the more people who never knew about this coordinate system, when we understood this global coordinate system or geodetic coordinate system with the earth center of mass, mean pole, everything. So people were working on the local coordinate system, which we call it local topocentric system. And this topocentric word means that your center is, or the origin of your coordinate system, which you assume for your work, is on the surface. So similarly, the origin is any point on the surface of Earth. Similarly, the three axes which we have to define, one becomes the north, one becomes the up, which is vertical upwards. North is the local horizontal plane, northing, easting, you can define it by a compass, local compass also. And obviously, because the advent of the GPS is that you have a global coordinate or a coordinate in a global system which you can relate every time. So that conversion is also possible by rotating this slide, the three axes and shifting to the particular center or the origin at the surface of Earth. So by making certain translation, by making certain reflection to make it left hand to right hand, and then rotating about the ECF axis so that you can get the local coordinate of your same point. So that are the three basic system. So conversion, I said, conversion from ECEF to local is also possible. We are more interested in this. So similarly, again, that we understood about the mean sea level as the equipotential surface, because the reason is people are more interested in finding the height with respect to their datum, local datum, which they have defined for their purpose, because the fluctuation of the geoid according to the continent. So the mean sea level, which defined as the particular equipotential surface, for call it local geoid. Similarly, the reference ellipsoid, which can be identified by these parameters, major axis, GM, which we call it gravitation constant, the J2 oblateness, and the rotation axis. So with this four mathematical parameter, this reference ellipsoid, which is a mathematical surface, can be assumed. Then this is the geoid and this is ellipsoid. So these are the two datums through which people are interested in finding their height. So this is one, I think the reference doesn't come up. It's a Wang and Solar paper in 2016, which is published in ASC. It's a very nice figure which relates the geodetic height, the orthometric height with respect to the ellipsoidal height by this geoidal undulation. So we have the two datum, which one is called it ellipsoid, another is the equipotential surfaces which are going on, and these are the ellipsoidal height to respective geoid. The figure doesn't come up completely. This geoidal height is with respect to the ellipsoid, and it is nothing but represented by capital N. So we have a relation between ellipsoidal height and geoidal, the height which is orthometric in nature, and by simple relation. So now people are developing the geoid model also, so that they can immediately derive the GPS derived heights, which we normally call it ellipsoidal height. So the work is currently going on, and many people are more interested in finding with their GPS receiver that what is the orthometric height at that point by using those model. Okay, so one popular, many of you may have heard of this system, World Geodetic System, which is defined by US Department of Defense for satellite positioning. The origin as the center of mass of whole Earth, which is solid ocean atmosphere. Similarly, the z-axis defined by the conventional terrestrial pole at this epoch. X-axis coincides with the zero meridian, this is this epoch, and y-axis makes the complete right-handed ECF coordinate system. So, and there are certain revisions which are going on for making this more accurate as the day progresses. So another one is the fact is this, that The ITRF, which we come to later on, what do we mean by ITRF? But it is defined by an international body which we call it IERS, which is International Earth Rotation Services. It defined the ITRF, but this W54 is defined by the US Department of Defense. So both two are, in terms of, we can make them in a similar category for, we call it as the reference frame. So this is, many people, before developing this W54, many people have this the local datum, which we call it local or regional ellipsoid, which are also, for our country we have Everest, which is somewhere it is in terms of Indian. So many people were previously, they're working on their own ellipsoid rather than a global ellipsoid. So yes, conversion is possible. We call it 7-parameter Helmert transformation from one datum to another datum by rotating, by translating, and by changing the scale. So yes, shifts, transformation from one ellipsoid to another ellipsoid is also possible, and those who want to do it, you can go through the literature and it will find it. Yes, this I must acknowledge the figures by Professor Herring. So this is interesting to know why these two figures are relevant, is because when you are on Earth, you don't see things or motion of the satellite just like this figure, isn't it? Because you understand the figure which is with respect to Earth fixed frame, and the satellites are moving in the space with respect to the geocenter of the Earth. So obviously you need to go to the space, or you think of a different fixed frame so that you could understand the Earth motion of satellite around Earth, and you have to measure the position of the satellite coordinate in those frames, those systems. So these two figures are much more relevant in terms of understanding why we need to go, or why do we need to leave our Earth as a reference or as a fixed frame. So instead of Earth fixed, Earth center, we have to move to some space fixed kind of frame, which we also call it, in the slide is coming as, so it is also coming as a space fixed coordinate system, which we also call a Earth centered inertial frame, which in which we need to understand, we need to understand this, the origin of this particular system is Earth center of mass. Pole, which we define as the angular momentum axis of, is that celestial ephemeris pole of, which we call it also Earth rotation axis coincide with this pole, this CEP. And the two fundamental planes are nothing but the celestial equator particular to CEP, the ecliptic equator, that is nothing but the Earth orbital plane. So just imagine the Earth in a space, and it is moving around the sun. So you could feel the Earth equator as well as its little shift in terms of relative to equator, so that the motion of Earth around sun could be clear. So that ecliptic path and this equator has a certain angle of shift, which is, we call it this shift is obliquity, which is nothing but 23.6 degrees. So the Earth, the gravitational attraction from Earth tries to shift that equator towards the ecliptic plane, and that's why we have major disturbance to that particular the polar axis, which we come to the next slide. And these coordinates, so the star measurement over this space coordinate system can be done on these two reference planes. One could be celestial equator, as well as one could be ecliptic plane. So if we do it on the celestial equator, we call it rise ascension and declination, and you could see that the celestial equator is this. So the right ascension and declination angle of this same star can be measured this in the ecliptic latitude and latitude format also. So the same star can have its position in ecliptic plane also, or the ecliptic coordinate system also, or we can refer it to in the right ascension and declination system also. So this is one way of referring different stars in the space in two different coordinate systems. Yes, as I said, because the Earth rotation axis is not stable. It is there are so many forces acting over it, and because of this, the Earth polar axis with respect to the inertial space, the motion of this axis we call it nutation, and it has certain two components which we call it long periodic secular precession and short periodic nutation, and that this shift, if the short periodic nutation are from 14 days up to 18.6 years. The period of this nutation is very short compared to the periodicity of this complete process which which we call it secular precession. And because of this, we have to apply certain correction when we move on from a space fixed coordinate system to the earth fixed system. And similarly, as the Professor Herring was talking in the first half, is that this is the figure which is available in many books, reference books, and you could see that the earth pole, reference pole, we call it the mean pole, or the pole which is changing direction from 1890 to the present 2002, and it is moving towards 2006. So it has certain shift in terms of its position. So we have to consider the polar motion or correction to the polar motion also when we are moving from space fixed to earth fixed system. Then, since this is the vector change of we call it the rotation vector of earth, and if we see the amplitude which is changing, because of this our time system changes. So there are vast literature is available on the time system, but I'll stick to some of the very relevant to the GPS. One is the atomic time scale, which is based on the frequency standard of the clocks which are available around the globe. And in this system which we are actually referring, or the satellites, there are atomic clocks on board. So one satellite have individual atomic clocks which is very stable, highly stable. And obviously we have our own time scales based on the earth rotation. So sidereal time, universal time, these are the two major time system which are based on the one with respect of distant star, another with respect to the sun. So sidereal time, when we are directly related to the earth rotation, not practical to measure the most earth application, and it measures the angle, our angle with respect to the zero meridian to a particular star, which we call it vernal equinox. So the so-called universal time, which is more practical as we are related to the apparent diurnal motion of sun about earth. So the two motion which we call it UT is the motion of universal time, is the apparent motion of sun around earth. So International Atomic Time, which is many agencies, we could find it TAI, or somewhere it is written IAT, both is same, International Atomic Time. And one TAI is nothing but the complete 86,400 second. It is very stable, and we want a relation with the atomic time with our local solar time, or we call it the universal time. Another slide on the sidereal time, which is nothing but relation with this true or the mean vernal equinox with respect to our local meridian as well as from the zero meridian. So there is one angle which is very relevant between conversion between ECI to ECEF, which is nothing but earth center inertial to earth center earth fix, is that the angle between the zero meridian to the so-called the apparent or the true vernal equinox. So there are four category. One, if you measure angle from zero meridian, we call it Greenwich apparent sidereal time towards the true. And if we go from local meridian, we call it LAST, which is local apparent sidereal time towards the mean or apparent vernal equinox. So this is a very good figure to explain all part of sidereal time systems, the four: GAST, LAST, GMST, and LM. So one G reference, if we go the reference as zero meridian, and if we take the local meridian, we have L. So universal time, obviously, because our polar axis is changing its speed, and because of which the day is either longer or shorter, but we don't actually feel it because of the efforts which were put in to account those corrections. So it is related to the apparent motion of sun around earth, and when referred to Greenwich meridian, we call it universal time. Obviously the R angle to the sun, and it is UT is not uniform because of that change in the polar axis of the polar motion. So when we correct our basic UT corrected for polar motion, we call it UT1, and the UT1 and TI relation is also unique. So we have introduced a new time system, or the so-called the USNO has introduced one new time system which we call it corrected for compromised UT, which we also called UTC, okay, coordinated universal time. So there are many definitions or many notations for this term, but eventually why it is helpful, because it actually relates with this atomic time, isn't it? By definition if the universal time which is corrected for polar motion and this UTC has changed, magnitude of its change is more than 9 seconds, a leap second is introduced in this UTC. So that will become more relevant to understanding why the different atomic time system are changed in terms of its values. So currently, what is the value of TI? We'll see in the next slide. So this is one good figure which could explain the UT and sidereal time. Universal time and sidereal time is that at the if this is your position on or observer position, and it is looking towards sun at the distant star, at the same time after certain period it will again come and see the sun and star. So it will again see the star 3 minutes 44 certain seconds before that you could see the sun. So that is the one relation between one complete sidereal day and solar day, which is nothing but, so sidereal day is 3 minutes 44 90 seconds. The difference is nothing but this, and so obviously the sidereal day is of this much second. So this is very nice figure which relates with the universal time and sidereal time. So this is the one reference on the leap seconds or understanding the atomic time with respect to the GPS time, is that this figure was drawn on this 11th of January 2018, and you could see that the 37 leap second has been introduced. So these are introduction of leap second to the UTC, and when this the magnitude of UT1 and UTC goes beyond 0.9 seconds, we introduce these kind of leap seconds. Okay, so why we understand the reference system? This is the summary why we are developing reference system for our own purpose, which we call it the understanding the GPS, because the satellite motion are related with the geocenter of mass, Earth, and that's why we need to understand the motion of satellite in its orbital plane also, as well as in the Earth center inertial frame also, because we have to relate these two systems to understand the position of our GPS station on the surface of Earth. So yes, it is essential for description of the satellite motion, modeling of observable, and as well as the interpretation of results. Then second is, we have to, since day by day the navigation system is developing a more or changing towards more accurate, we have to define a system as also as accurate one. So yes, the reference system is nothing but where we assume that this is how our origin would look like, this is how our fundamental axis will look like, but the reference frame are the actual one which helps our cause in realizing those reference system. So reference frame and reference system are two major important quantity here, is that you help the reference system which are available are helping in realization of those reference system. So every coordinate system which we are saying is related with a particular reference frame, and obviously certain conventions are drawn based on which we define our system. That's why the notation comes as conventional reference system. Why do we need a reference frame? We actually need to fix those frame in terms of understanding those parameters, so that when we change from one coordinate system to another, we have those parameters before our hand with the what is the translation, what is the rotation, and what is the scale. And so space fixed, so in general we categorize these into two fundamental systems, as one is a space fixed, which we call it conventional inertial reference system, or CIS, for description of the satellite motion. Second is earth fixed, for our own purpose, is that we call it conventional terrestrial reference system, which we call it CTS, for position of observation of a station. So you could by looking at the slide, you could easily relate that, okay, one system is helpful in realizing the motion of the satellite which is orbiting around the sun, and one system is helpful in defining our position. So obviously you cannot work in two systems, isn't it? So when you are finding the position of your station or your observation station, you have to make a position in this system, which is earth fixed. And then obviously if you have understood this space fixed system, you have to convert the position of satellite in that from that space fixed to earth fixed, so that you can easily relate these two coordinates. So summary, yes, the position, it can be either in space fixed or it can be in terrestrial, which is earth fixed. Obviously the time, which is also important, so that it is related with the quantum physics or with the earth rotation. So reference system and reference frame. Summary is that reference system is set of prescription, convention, and models required to define any time the triad of axis, origin, as well as reference frame is nothing but the practical means to realize it. So you have to realize your coordinate system by defining the frame. So terrestrial reference system and terrestrial reference frame, both are nothing but we can realize from one to other. And this is the ideal reference frame, which should be like this, which is very easy to understand because of your imagination is that geocentric should be geocentric in nature. The z-axis is direction of Earth rotation. However, it is not easy to realize because the pole is changing directions throughout the year, day by day, because of the effects which are from the different planets. So the two system which we call it conventional celestial reference system, which has origin, which have pointing towards vernal equinox as its x-axis. The angular momentum axis becomes the z-axis. Similarly, we have CTRS, which is nothing but the conventional terrestrial reference system, which is nothing but x is pointing towards the Greenwich meridian and the mean pole as its z-axis, and these two systems are the backbone of the GPS. So conventional system, as I explained in the previous slide, is nothing but the position of Earth angular momentum axis in the celestial inertial frame. X points to vernal equinox, and obviously when we understand this, we have to understand that these frames which are helping in realization of these two systems is that these are nothing but the fundamental when we say the terrestrial system, the terrestrial frame is nothing but the set of points which are globally distributed and well measured. When I say well measured, they are measured even by the different space geodetic techniques, which are not only GPS, we use SLR also, we use very long baseline interferometry also for these measurements. So first realization by international body, as I said, the so-called IERS in 1995. Then similarly we have a conventional terrestrial system, and it is metallized by a set of ground control points of precisely known position and velocity, which establishes the TRF. And obviously the conventional inertial system, obviously the frame is associated with this conventional inertial system also, and it is materialized by precise equatorial coordinate or of extra galactic radio sources. So you could differentiate the two catalogs, isn't it? One, when we are realizing our own terrestrial system, we have set of points which are globally distributed on the Earth. However, in the first case, we are actually managing the radio sources, isn't? We are measuring those radio sources and we are making a catalog of it. So this is how your celestial international celestial ICRF, which is popularly known as, this how your ICRF looks like, and this is your ITRS look like. So as I said, it is not only measured by only one technique, it is measured by multiple techniques, and these techniques are very precise in terms of its measurement. So, and obviously when we convert from one coordinate system to another, which we also call it from the so-called celestial reference system to terrestrial reference system, we actually define it by the orientation. Earth orientation parameters are given by the international agency, which are helpful in understanding, and conversion from one system to another system is possible from celestial to terrestrial. And these are nothing but the one simple figure which could properly explain the conversion from one the celestial system towards the terrestrial system. However, it is not easy to realize just by one explanation or one lecture. What you have to understand is that we are somewhere in the inertial frame. We have our coordinate, or the coordinate of the satellite is available in the inertial system. We have to convert in our terrestrial system by using these rotation metrics, and by there is no translation because the center of mass of Earth is fixed for both as the origin. So there is no translation, but we have to correct for precession, and the equations are available for precession, where the equations are available in literature where we can use it. You have to correct for nutation. Please remember, these are the physical phenomena, isn't it? They are not errors. We have to correct for those phenomena, and you have to convert from ECI to ECF by this Greenwich apparent sidereal time. You could relate with this previous figure which I was showing, that from 0 meridian to that the true position of the equinox, which we call it Greenwich apparent sidereal time. So the rotation are applied from, so that the coordinates of satellite which are converted from the terrestrial systems, and the last two rotation are nothing but the rotation for the polar motion, because when you convert from your so-called the inertial system towards terrestrial system, you cannot directly meet the mean pole, which is for the ITRS, isn't it? So it is little shifted in terms of its polar position. So you have to rotate so that it will eventually meet this point. And many literature is also seen that in many literature it is also written that the pole of both two ECI as well as ECEF are same. So many literature are also written this, but eventually this is the complete rotation matrices for the two system from inertial to the so-called terrestrial system. So coming back to the our own why we are here, so that we have a GPS, and we are not covering the history of GPS. Instead, we are directly arriving at what was the design objective of the GPS, and it is nothing but to derive at a global navigation system which could helpful and which could be seen in throughout 24 hours throughout a day from a particular position. So suitable for different platform, aircraft, ship, land-based and space, able to handle a wide variety of dynamics, real-time positioning, velocity and time determination, as Professor Herring said in the first half, is instead of making the position estimates throughout the time, you have to estimate the velocity also, and as well as the time estimation in different capacity. So position results available in single global geodetic datum, so that people from India can relate with the people of US, so that how the time or coordinate changes. So that is one possible design objective, is that it should be resistant to jamming, redundancy provision to ensure survivability of the system, ability to provide service to unlimited number of users and worldwide, which is actually possible nowadays. So it is Navstar says navigation, satellite, timing and ranging, and it's also known as short form is, its complete form is Navstar GPS, we call it GPS simply. So it is satellite, radio based, radio positioning and time transfer system designed, deployed and operated by US Department of Defense. Should be thankful for. And obviously the design to take over from existing, the previous, from transit system, which was the previous system before GPS. So designed to take from the existing navigation system to be supplied to each man in the field. And three segments, popular segments. I'll not cover much on individual capacity of the segment, but you will be happy to see that three segment, major segment of GPS is that one is a space segment, where all the information about the satellites is available, orbits, location, position of the satellite in different orbits. Second is the control segment, and third is the user segment. So whenever you read a literature of GPS, people say it is not a two-way system, it is a one-way system. Only GPS communicates, GPS satellites communicates, and you the signal, and you receive the signal through the receiver, GPS receiver, and you use those signal for making measurements in terms of position. However, it is a two-way system for the control segment and space segment, where the control segment actually talks to satellite. You know, you are the user segment, so you don't talk to satellite, but the control segment is all ears and eyes and ears of the GPS satellite. They actually tell the satellite that where should you move, how much your velocity should be. This is how they, in general layman language, you could understand it. So that control segment is that's why the name is control. It is all eyes and ears of this this GPS system, and obviously user, we only use it for our own purposes. So space segment is nothing but satellite constellation which downlinks the data, which is nothing but coded ranging signal, position information of its position in the orbits in terms of certain parameters, not directly the position, atmospheric data in the space, almanac also. So one by one we'll explain these components in the slides which are coming in next few days. What do we mean by almanac? Almanac is nothing but information about all other satellite in the orbit constellation. So let's say you people are the satellites of this class. So it is, almanac is saying that one person knows information about all other people in the class. So similarly, it is nothing but the information about the all satellite, and every satellite sends this information to the user. Atmospheric data is also sent in terms of certain parameter. We'll come to that in the next few slides. Position of information in terms of parameter, not directly it is telling you XYZ, it is telling you in terms of parameter. We will call it navigation message. That will be also explained later on. So basic function of satellite is nothing but receive, store information transmitted by the control station. So please focus on this line, is it saying receive and store information transmitted by control stations. That control station control segment is helping the satellite so that it becomes fit, healthy, so that it delivers the right message to the users. So maintain very accurate time by means of 2 cesium and 2 rubidium oscillator atomic clocks on board. Transmit information to user with the help of signal message, which we call it navigation message also. and maneuver to position space by thruster control segment. So control segment is actually helping the satellites to move in the orbits. So this is how the satellites were launched in different block 1, 2, advanced, replenishment, replenishment modernized, follow on, and block 3rd. So those who are interested can go on to find the literature on each block, because every block has certain pluses and minuses. So because they are also developing the complete navigation system for users, so in block 1 certain limitations were there and fails were there, so it was removed and follow on. So full so 2 operation capability were there. So initial operation capability were launched in somewhere in 1993. So full operation capability were declared on 8 December 1993 when there was 24 satellites working in block 1, 2 and 2nd A. This is the bird cage of the famous GPS satellite system. So it has 6 orbital planes, and each orbital plane has certain 4 satellites, and in each figure, each satellite is identified with 2 character codes, a letter identified for the orbit A, B, C, D, E through F, and E1 becomes the first satellite in E orbit, second satellite E2 becomes second satellite in E orbit, similarly on. So this is one nice figure of understanding this the complete constellation of orbits of satellites in the orbits. And as I said, the control segment is all eyes and ears of the satellite system. So master control station, also known as Consolidated Space Operations Center, which is CSOC. So it is located near Colorado Springs, Colorado, and master control station collects all data from all monitoring station. It processes it and it sent to uplink station so that it could be sent to satellites. So obviously there are 2 major features of this from the MCS, which can also implement a controlling methodology or tweaking the satellite clock, which we call it selective availability, which provide only a limited access to particular users. So from 1 May 2000 essay was put out. Sir was saying in the first half is that if your clock information is poor, that means if you have error in your clock is of microseconds, so that you could calculate if the position changes, the satellite is moving with certain 3 kilometers per second. So you could see that with the microsecond error in your clock, you are nowhere on the earth. You are somewhere beneath the earth, isn't it? If you are calculating the range. So it is nothing but, in summary, the control segment is all eyes and ears of GPS and monitor satellite by measuring distances to them. So this is general figure or the common figure which you could easily relate. So there are certain monitoring stations. The monitoring station collects the data throughout the day from the GPS satellites. It's collect data and send to master control station. It process, and if you see written is prediction of ephemerides and clock behavior. So it is because essentially satellite is sending their own information in terms of its position to user. So those ephemerides, which are nothing but the orbital parameter, are updated, predicted, and they are uploaded again onto the satellite. So again, when they upload the information to the satellite, so now satellite is sending you the right information, isn't it? Because at the 20,800 kilometer away from the Earth space, there are so many forces acting on the satellites to move it away from the orbits, to move it to disturb its motion in this orbit. So obviously, if control station is there, then only it would be helpful to have a right information through navigation message, and that's why the 3 segments, in one of the segment which is control station, a control segment is very much useful. So these are the location of the monitoring station as well as the master control station. Some more are adding on in the future. Obviously, you are the user. However you want it, you want to place it on the vehicle, on your hand, on your pocket, and on your watch. Everywhere you want your GPS. So user are using it through handheld radio receiver, and it is nothing but measure the time from the radio signal to travel from GPS satellite until it arrives the GPS antenna. So obviously, the second line, which is nothing but calculating the pseudo ranges, is the fundamental observable of the GPS system. We'll see in later on the few slides that what are the prime observable of GPS system, how we are using it, how the mathematical modeling can be done, and what could be the mathematical modeling behind the GAMIT, which you could relate to. So current status, the question was, do you know the wavelength of the radio signal? So yes, although there are more signals are coming up, But in general, L1 and L2, two signals are available, one at 1525.42 megahertz, another is L2, which is 1227.60 megahertz, and L1 sends CA code and P code, which is modulated on, I think it is written wrong. Yes, it is right. Okay, L2 only send P code, not CA code, and obviously the WGS84, which is Earth Center Earth Fixed, is the global coordinate reference through which you could get your coordinates. The current satellite segment, and as on 1 January 2012, it has the capability anti-spoofing selective availability. So selective availability was off, but anti-spoofing has been there from since 1994. So it is nothing but the encryption of the very precise P code. The name P code, although we'll cover it in the next few slides, what do you mean by P code, course acquisition code, or P code, precise code, so which has only military can access to this P code, or the authorized user only access this P code. That's why in order to make this P code not vulnerable for different purposes, the control segments or the US Department of Defense has anti-spoofing facility which encrypt this P code and becomes a Y code. So advantage, yes, intervisibility between station is not necessary when you can have GPS at this location in your body, and you have GPS at your place or your institute also, and you can do your work. So independent of weather condition as a result of using radio frequency to transmit the signals. If the same field data detection procedure are used, position accuracy is largely a function of baseline, which we talking about in the first half, is that baseline between these two stations. One is your location, another is maybe IGS station or another receiver. So because of these two advantages, many people are using it. You can follow your lecture slides also, where you can read more about advantages. Certain limitations are also there, as I was saying, that maybe in future you will have access to the receiver which is very precise in terms of giving, or it has a dual frequency geodetic receiver which is now more than $30,000 US, and in future you will have access to it in less than $2,000. But nowadays if you have to get the higher accurate data, highly precise data, you have to choose high efficiency, and its efficiency has a price. So costly, it is also costly if you go for dual frequency receivers. Handheld receiver are very cheap, you can now access to in less than 35,000 Indian rupees. And because in station intervisibility is not necessary, GPS is particularly attractive technology for used in in terrain. However, the logistic problem for transporting and supporting. So if you are going for taking the data to a hill, you have to climb it with your station and put it there. So it is also a difficult job to do, but you have to do the field work also at the same time. So obviously this is a little issue which we whenever we read literature on GPS, is that vertical information is not provided in height system generally required, because we are more prone to use height system in our local mean sea level or local system in terms of geoid, local geoid, but GPS is providing height with respect to ellipsoid. So you have to, are you aware of this the geoid model? You can convert from these two systems. Today, all people expected to use it for variety of applications. Accuracy and reliability almost taken for granted. Satellite 20,000 kilometers of Earth, code measurement centimeter, phase measurement to mm. Whenever someone is saying GPS gives the data in millimeter, what are those observable which are actually helping us in giving the result in mm level? It is nothing but the carrier phase measurement. So the carrier over which the information is modulated or the codes are modulated. So when we reconstruct the carrier, it is actually helping us in the millimeter level precision. So yes, today the examples we are discussing with this GYAN course also, how do we get this measurement millimeter level precision in our position estimates? But counting those so much errors from that space to Earth, there are so many errors which we have to account for, and the GAMIT is accounting all possible errors which could be there from space till we arrive at this signal at this your point at the antenna. You have to correct for it. So I think how much time is it? 3:05. We have 10 minutes. So a little information about satellite, which you will be covering. So The Kepler's law, you can read from the literature what are the Kepler's law, but for these understanding the satellite motion around orbit, you have to understand these three laws. One is ellipse, orbit of each planet is ellipse with the sun as one of the foci when they developed this the Kepler's law. Second is law of equal areas. Obviously, you could consider that position of any satellite moving on this path and this path becomes, the area becomes equal. Third is the relation of the orbital period with the semi-major axis. So this is certain notations are very important, because when you read the navigation message, these are the informations which are provided in terms of certain parameters. So we'll see what information is actually provided, but perigee, which we call it point on elliptical path, right, where closest to Earth's surface. So closest to Earth's surface become perigee. This is apogee, which is the farthest point. So line of epsite, line connecting perigee and apogee. Ascending node is nothing but where the satellite comes from south to north, that becomes the connection, the point becomes ascending node, and when it goes to north pole to south pole, it becomes the descending. So line of nodes also, it join the two nodes. These are the Keplerian or parameter which are given by the satellite through navigation message, which is nothing but the semi-major axis of those orbits where the GPS satellite is presently moving, eccentricity of that ellipse, inclination with respect to the equatorial plane of the orbits, right ascension. As I said, right ascension is a method in a ECI system, which is Earth Center Inertial System. So right ascension of ascending node, argument of perigee, will come to those notations also in the next few slides, and the time of perigee passes or alternate anomaly, which is nothing but the position of the satellite in the orbit with respect to the line joining Earth foci and the perigee. So these are nothing but those very nice figures of explanation of these parameters. So this is how you understand. Please remember, this is why we are discussing the reference system in the first part, is that the motion of the satellite we are computing in terms of coordinate, but it is not in Earth center it is not the terrestrial system, it is the Earth center inertial system. Please remember, we are measuring the satellite coordinate in Earth centered inertial system, and we have to rotate it further or use the rotation matrix to convert into Earth center, Earth fixed. And these are the forces which are acting on which are disturbing actually the satellite motion in its orbit. It's nothing but the attraction of the Earth, third party atmospheric drag forces, solar radiation pressure, magnetic forces. So these are actually disturbing the motion in general of the satellites. And as you can see from this very nice graphic, this is your satellite in a particular orbit. These are the foci. On one of the foci is the Earth. Please see very carefully, and which we call it the nearest position of the satellite. This is perigee, another is apogee, and this is anomaly to anomaly. This is the position vector to that satellite. So normally people understand this conversion not directly from the ECI to ECF. Instead, they said that first I will estimate the position of satellite in orbital plane. So that would be easy because it is a 2D plane. Satellite is not away from that orbit, it is moving in the orbit. So it is a 2D system. So they generally want they calculate the position of satellite in the orbital plane, then they change the position of those estimate from orbital to ECI, then they changes from ECI to ECF. So we'll see that also. So their axis, eccentricity, another thing. This is your equatorial plane. This is the satellite path in the orbits. This becomes the, we consider that this is the south and it goes to north. So that becomes ascending node, and this is the perigee. This is the vector to the satellite, the ascending node, line joining ascending node. This is the argument of perigee. This is the angle we are drawing, the three axes x, y, z. This is again right ascension of the ascending node. So when I say right ascension of the ascending node, obviously the x will not be of terrestrial system, it would be of celestial system or ECF. So this is the inclination with respect to the so-called equatorial plane. And these are those wonderful equations which we could relate when we are converting to conversion to earth fixed XYZ. So you could see that the change are nothing but, first we get the 0 says that in orbital plane it is nothing but we have 2D system. So the angles are nothing but omega plus V, which we call it omega plus F, which for the anomaly, and we compute the earth centered space fixed. The conversion is available from earth centered to earth fixed, we have to convert it again. So this is the one, although it looks a little tricky to understand it, but it's very easy to when you go through the literature in details. So with slide gone on to be broadcast orbits, the orbital information which is sent by the satellite to the earth receiver on the earth, and broadcast, and when it is given to you by some third agency, and which in our case has become the IGS products, which we call it a precise orbit, which is very precise. All errors are accounted, and luckily the XYZ, the information of satellite in precise orbit is given in terms of XYZ in ECEF. So obviously the literature says that you have to consider the broadcast orbits when you are the one who computes the position of satellite in the different systems, either it is ECI or ECF. You have to consider all parameters, all Keplerian parameters, as well as the forces, the constants which are given for the consideration of those forces. And then it is 6 elements per satellite, 3 clock parameters per satellite, 3 solar pressure coefficient per satellite, 2 clock parameters. So you see that there are every possible parameter which could be helpful for realization of its health status and its position in the space will be transmitted to or modulated onto the carrier to you. And obviously the precise orbits are nothing but nowadays in a few minutes the data is available which you could download and use it in terms of estimating the satellite position in XYZ directly. So IGS usually nowadays also, if you go in the lab, you will make a folder of IGS, which is nothing but the orbital file which is downloaded from the shget.org from those FTP. So the IGS orbits are nothing but which is GPS ephemeris and values tabulated at 15-minute interval at each for each SP3 format. SP3 is easy to relate with your chemistry, where you try to develop the which in terms of where it is. Yes. So geocentric station coordinates and velocities, earth orientation parameters. So these are the core IGS products, and this is one tabulated in a tabulation manner. You could see that ultra rapid, final, and these are available on in terms of the satellite ephemerides, satellite clocks, earth rotation parameters. So every information is also available on FTP by the which we call it IGS products. So international agencies are giving us this data so that you could improve your results if you don't have access to or you don't know how to use the broadcast. So it's a summary of the 3 parameters: time, Keplerian, the perturbation parameter. Again, the summary of all the 3 broadcast ephemeris parameters. And this is the forces which I was talking about. So changes in inclination also we consider the forces of the position of reference epoch. So these are the basic figure which we consider for understanding the motion of satellite in space. So the content for this presentation, I'm thankful to these people for I'm using some of figures from this the lecture content. Thank you. So as I said, the questions. So as I said in the first half is that although it is the understanding of GPS is not a day process or an hour process, it is a continuous process. So I have been reading the GPS material from 2011 onwards. So by the 6 years I have understood some of the basics which were helpful in understanding my work, my research which we are doing at MNNIT. So it is a continuous process. So obviously in one lecture slide, which is a very concise one, you cannot understand it completely, but you have to read enough so that this becomes more understandable. So we have to move, we'll have a 10 minutes break, not more than 10 minutes. We'll have to shift to our lab for GAMIT session, where your PCs or machines are being ready for this. And in 10 minutes break, you'll take your places in the lab just front of this classroom. Okay?